Okay, well, it looks like Monday at 2 o'clock has rolled around again, so it's Bill Gillespie here again to talk about some Bayesian modeling and simulation. I guess if somebody wants to jump in, maybe just confirm that they're getting the audio okay or not. And I'll go ahead and start getting this thing rolling. Okay. Okay, well, sorry to miss you all last week. Hopefully you were able to get to the recordings okay. But I'm back in the saddle and we're in real time now. And today the focus is going to be on Bayesian model evaluation and comparison. And I think that'll probably cover the whole lecture. We'll see if we have time left over. We can tweak into some BUGSModelLibrary stuff. And I guess start out before I jump into this and mention that in the Bayesian literature, there's sort of multiple philosophical and methodological streams about model checking and model comparison and model selection. There's at least one stream that sees a model selection and model checking process as being almost contrary to I guess a sort of purist philosophy of Bayesian inference. My own view on that is that's probably not a particularly logical stance to take in real data analysis, but there are a few folks like that. There are some that go down a sort of decision analytic strategy for dealing with it, and some of that's interesting, but some of it can be fairly difficult to implement. The path I'm going to take is the approach that's suggested by Andrew Gelman and a few of his like-minded Bayesian statisticians. And in fact, I'll point you to their text again. Recall that one of the texts I mentioned at the outset was a book called Bayesian Data Analysis, where Andrew Gelman is the first author, and then there's also John Carlin, Hal Stern, and Donald Rubin as co-authors on that. And chapter 6 in particular talks about the title of it is Model Checking and Improvement, and much of what I'll be talking about today is either drawn from or is otherwise fairly consistent with that chapter, and that's the approach I'll be taking, so I'd encourage you to take a look at that. So let's go ahead and jump into it. Let's start out with an attempt to describe at least one possible ideal for Bayesian model evaluation and comparison. And that would be one where you start right from the outset with I guess, sort of a supermodel that would be a mixture of all possible true models. True in quotes, because let's face it, we know none of them are, but you would be a mixture of all possible true models or all possible plausible models, if you prefer, and that would also include all known substantive information, and that would be both the information and knowledge that goes into the model structure, but it would also be the quantitative information that might appear in the form of prior distributions within the model. And if you start with that kind of an approach, that would extend the Bayesian notion of modeling uncertainty to include uncertainty not just in the parameters, but also uncertainty in the model structure itself, so that you end up with sort of a grand mixture model that contains all the models that you might be interested in, and there's a probability associated with every possible model within that grand mixture model. And if you were able to come up with such a thing, well, then these tasks of like model evaluation, model comparison, and sensitivity analysis all can be handled within a single analysis. And in particular, once you have the posterior distribution for, in effect, all the individual models as well as the probabilities associated with each one of the models, you basically get all of those kinds of applications built in. So as I'm saying here, each model in the mixture then is associated with a posterior probability that it is the true, or in some sense the best model, and that provides a metric for comparing models, since you can compare those probabilities. In addition, sensitivity to your model choice then is obtained by comparing model-specific, or if you like, submodel-specific posterior predictions. So you get your sensitivity analysis there, and as I say in the previous bullet there, by comparing those probabilities, that gives you your model comparison as part of that, and you could possibly also use that as a model selection criteria in there. Now, this is something of a, I guess, of a modest proposal here, in that it's an ideal that can't be achieved in full in any reasonable context I can think of. You can only sort of approach it via practical compromises, and in effect that's kind of where we're going to come from, is that yes, this is sort of the ideal that we might like to be able to use. We know we can't realistically do that, but there are there are reasonable compromises that at least what shall we say, that have ambitions towards this kind of an approach, and that's what we're going to be looking at here. So, a philosophical consequence of the ideal that could be translated into into a more pragmatic approach is what we'll talk about. So, one of the consequences here is in the Bayesian literature, we tend to see that model selection is often avoided in favor of using, well, if not a full model like the ideal, what I just sort of put here is a fuller model that contains potential competing models as special cases. So we may not go for that grand supermodel, but we might be able to come up with something sort of in between. So it might still contain multiple candidate models within the overall model. As I mentioned here, what is particularly avoided is what we have seen as the classical approach of performing a sequence of hypothesis tests. For example, the sort of classical approaches for doing covariate selection that we encounter with both linear and nonlinear models is in effect a sequence of hypothesis tests to identify what is in some sense an optimal set of covariates. Then the other aspect here is that this fuller model approach then acknowledges and quantifies the uncertainty in the relative correctness of competing models. And there's different sort of categories of these so-called fuller models. One type of such model would be a discrete mixture model. This would be one where you would have some finite sequence of potential models, and I've indicated the models in terms of calling them M1, M2, M3, and so on up to some Mn here, some finite list. And so for each one of those models has a likelihood associated with it. So you can see those listed all across here. So we've got some probability of y given the model's parameters and the specific model in here, and then that's multiplied by the corresponding probability that that model is in some sense the correct or best model of that list. And so you end up with this overall likelihood for that. And then, of course, you'd have priors for all of the various parameters, some of which would be distinct for different models as part of that process. So, example of something like this that you might see would be, there's big literature, for instance, of mixtures of normal distributions. So you might have a collection of, you might model something with a collection of normal distributions with a discrete list of different means for those normal distributions, possibly also a discrete list of standard deviations in them. So you would end up with a sum something like this, and each one of those normals would be weighted by a corresponding probability term. So that would be the case where you have a discrete set of models. Another case would be one that could be termed a continuous mixture model, And I guess one example of that would be if let's say you're doing a model where you have a collection of covariates you want to consider. If you simply use sort of your full model that contains all of the covariates of potential interest, each one of the covariates involving a coefficient, also possibly including interaction terms with coefficients associated with the interactions. Well, those coefficients, by being able to take on a range of values, essentially allows you to make a sort of a continuous selection across all of the, so you don't simply throw out the covariates or anything, or test models with different collections of covariates. You simply leave them all in, leave all the coefficients in, and that's essentially giving you a simple continuous sliding scale for all of the covariates within the model. So so that's one direction one can go in here, is to actually consider multiple models within the framework of a single mixture model. Now, even that can often be difficult to accomplish, particularly in an MC framework, where when you start getting multiple models, some of which may introduce some serious convergence problems with a tool like that, or with or with an optimization method like maximum likelihood too. That's often a problem there too. Often a more practical approach is not to go to too grand a mixture and to simplify things a bit. So what I'll do here is attempt to describe what I term a typical practical Bayesian model development process, and as part of that there are elements of model checking and model comparison. So what I'm imagining here is we start out by proposing some initial model structure based upon the available prior information, and as I say here in the sub-bullet, realistically exploratory analysis of the new data also influences that process. If we wanted to be real hardcore purists, choice of model structure and data analysis in a sense would be somewhat separated, but realistically we're usually still learning at the point where we're bringing where we're doing model development in here. So unless you're doing sort of more of a confirmatory assessment of a particular model, you're probably going to be doing some exploratory model development work that includes, as I say, some exploratory analysis of the new data itself. So, but either way, the idea, you start out with proposing an initial model structure based upon your available prior information that's going to it's going to be describing both the structure. This is also the point where you're going to be identifying suitable prior distributions for the various model parameters. Then, of course, you analyze the data and assess whether the model is consistent with the data and prior information. The kinds of tools we'll look at for that, one major category of methods is going to be posterior predictive checking. But in addition, we should be asking whether the model inferences, predictions, and values of parameters and other derived quantities are really consistent with other knowledge. By other knowledge, I mean, if you have a model, let's say the model itself has some mechanistic elements, and some of the parameters or derived quantities are things which theoretically ought to be consistent with some known, say, physiologic or otherwise mechanistic quantities. Well, are they? Or are you getting numbers that are clearly implausible given what else you know, at which point you have to start questioning whether either your model structure or the data are appropriate at that point. So part of this is database. The posterior predictive checking is really a database model checking process where you're focusing on comparisons to the data at hand, in particular the data that you were analyzing, whereas the second bullet point here, where we're asking whether the inferences, predictions, and values are consistent with other quantities, I'm thinking more about comparing that kind of information with prior knowledge that existed before you had observed the new data. Another type of thing you're going to want to do is assess sensitivity to potentially influential assumptions. And of course, the biggie that we encounter with Bayesian analysis is going to be your choice of prior distributions. So we look across those sorts of that kind of model checking, and ask ourselves, you know, are there some deficiencies here? Are they significant enough that they could adversely affect important inferences? And if the answer is yes, then we should probably explore model revisions. And once we've identified what we think is a new model candidate that will remedy those problems, we then go ahead and analyze the data, go through the model checking process again. So it's inherently an iterative process in that sense. But the difference here is, I guess, we're not talking about the formal hypothesis testing in order to somehow select what we think of as an optimal model. We start out with what we think is what we hope right from the outset is an optimal model, and critique it as we go, and only revise the model if we find deficiencies. I guess one area where that would be, well, one place that we would encounter that a lot in pharmacokinetics, again, is in, for instance, the covariate identification process. The approach that we actually commonly use at Metrum is not the classical covariate selection process based upon things like forward addition, backward elimination or whatever. It's instead the approach we use is to identify in conjunction with the key stakeholders the most relevant covariates, the ones which there is reason to think there might be an effect, or simply ones for which we want to ask the question of whether or not there's an effect. We construct a full model that includes all of those covariates and then assesses their influence on the model. But at that point, you evaluate that, but they stay in place. You don't. There isn't an elimination process in that sort of full covariate modeling approach. And of course, once you decide you've got a suitable model, then you use that model resulting from this process for your pre-planned inferences. But of course, in any practical modeling context, questions come up along the way. There may be what I term here some hypothesis generating activities that come out of the entire model development process. So there may be some additional data mining efforts to explore the influence of covariates that weren't considered in the original model, for example. Perhaps various alternative model structures that weren't considered in the previous sensitivity analysis. Some of this might be done because we're trying to improve the model we have. Some of it may simply be done to evaluate that previous model and create tools that we need to defend it in the presence of other criticism. Okay, and what I want to do is get a little more mechanical now. Recall that one of the steps I mentioned in here as part of the model checking here was the posterior predictive checking, and that's what we're going to visit now. Let's talk about some posterior predictive checking. Well, first of all, I guess the name posterior, of course, means these are things that somehow involve the posterior distributions, and since we're talking about posterior predictive, we're talking about posterior predictions. So we're talking about things like posterior predictions of observations or of derived quantities based upon those predicted observations. So, and we are going to be checking those predictions against either the same data that was used for the analysis, or we may also use that to compare it to data that has not been used as part of the analysis. But either way, we'll lump that under the general heading of posterior predictive checking. The kinds of checks we're talking about, most of the ones we'll talk about fall under the heading of graphical checks. So for example, some of them compare data and predictions of that same data. Some of them compare what you might consider sort of derived statistics from the data, what I termed here data summaries, and compare those data summaries to model predicted values of those data summaries. And finally, there may also be some residual analysis, which is, I don't know if that's so formally considered posterior predictive checking, but residual analysis is still part of the package here to assess elements of your model performance and whether or not it's consistent with the data. In some cases, you may choose to use actual formal numerical checks that fall under the heading of posterior predictive checking, and there's a term out there sometimes referred to as posterior predictive p-values, where you may essentially calculate the probability that that your test statistic is, trying to figure out the best way to term this. I should have thought about this beforehand. But it's essentially the probability that the observed test statistic could have come from a model consistent with the one you're using. And, well, we'll talk more specifically about what that is when we actually get there. Excuse me. Okay, let's start out with sort of the basic graphical checks, and you've seen these already in the examples we've been doing. In fact, the ones that you're looking at here are actually lifted from last week's hands-on example, good old hands-on example number 2. And so right now I'm just looking at graphical checks where I compare model predictions of the data to the observed data. So we simply take, I guess, what we think of as kind of being the raw data, the things that end up on the left-hand side of our likelihood function. We're actually modeling this. So on the left-hand side, for example, here I've got the y-axis is showing the inhibition of factor 10a activity, and the x-axis here is our time. And again, recall this is some data from, it's one of the treatment arms. You can see we're from the 40 milligram treatment arm from the data we used for the last hands-on example. And you can see the circles on here, and on each panel here is a different individual. So we're looking at the time courses of this biomarker. And you can see the data, and then the blue curves here are posterior medians, or again more correctly it's the medians of the predictions based upon the MCMC samples, and then the dotted red curves on either side of it then represent the 5th and the 95th percentiles of our posterior predictions. Thus they represent a point-wise 90% credible interval then for our predictions. So we can look at these, we can sort of ask, okay, well, is approximately 90% of our data actually enclosed within those prediction intervals? And that's more or less what we expect 90% or more actually to be enclosed within those bounds. And certainly just based on eyeball here for this subset of the data, that appears to be more or less the case. The one on the right-hand side is a little bit more comprehensive in that what I've taken is the data. This is actually for all of the data that we used for that example. On the y-axis here, again, we've got our inhibition of factor 10a activity in percent. And on the x-axis now we've got Me2 plasma concentration. So we've now got all of the data for all of the individuals plotted on here, so you can see a very dense collection. And overlaid on that, then we've got our median concentration response curve here, and the 90% credible intervals about that. So that would be, again, that'd be a slightly more comprehensive sort of posterior predictive check in here. Actually, one thing let's see, do I say? I guess I do say this. I've noticed I've also making a distinction here in that on the left-hand side, I'm looking at individual predictions. In other words, the posterior predictions here represent prediction of new observations in the same subjects along here. Whereas on the right-hand side, you can see on top, I've referred to this as population predictions. And in this case, the 90% credible interval is enclosing what would amount to a 90% probability region for predictions of new observations in new patients. So these bounds would be somewhat wider than if we were making predictions for a specific individual. And I guess you may want to get this picture in your head here, the one on the right-hand side. That's actually part of our homework that I'll be giving you today will be to create a plot something like that. Okay, and here's some slightly different category of posterior predictive check here, where instead of comparing directly to the data, we're going to take the data and create some sort of a data summary or statistic from the data. And in particular, the ones I'm looking at on this page here is we're going to take that factor 10A activity, and we're taking a look at the time courses, and we'll calculate a peak and an AUC. So in fact, let me go back to the previous plot here. Sorry, we jumped ahead. There we go. So if we take, say, one of these curves over here, what we're talking about doing then is, in one case, we're talking about taking a peak from the observed data for a given patient, and then taking the mean over all the patients in a particular treatment arm. And then the other example will be taking the area under the curve, just taking the trapezoidal rule over 24 hours, so we'll just make it a truncated area under the curve. And doing that again for each patient, and then taking a mean over all the patients. So the statistic or data summary of interest then will either be a mean peak factor 10A inhibition or a mean AUC factor 10A inhibition. Go back to that slide. So we've got now something which is a derived quantity from our observed data. And then we do our posterior predictions for the observed data. And for each posterior sample, we calculate the same statistic. And then look at the posterior distribution of that statistic and compare it to the value for the observed data. So let's take a look at the left-hand side. Okay, we're looking at plots here, which are density plots. So what we've done is taken all of the data and then estimated a density for that quantity. And you can see in the left-hand panels here, we're talking about the mean peak inhibition of factor 10A activity. So for the observed data, you'll see for each one of our treatment arms, there's a vertical dash red line. So that's right at the value that's calculated then for the observed data. And again, since what we're doing, we calculate a value for each individual and then take the mean over all the individuals in that particular treatment arm. So for each treatment arm, we just get a single value. But now for the posterior distribution, or our MCMC samples that approximate that distribution, for each MCMC sample, we have a whole vector of predicted values. So for all of our individuals, we have predicted values for each one of those samples. So we go and calculate the mean peak. Well, we calculate the peak for each individual for the predicted values, calculate the mean of those peaks, again by treatment arm. And so for each one of those samples, we'll get a single value, and then we can look then at the distribution across all of those MC samples, and that's what generates the distribution we see as a density here. And then we can ask, well, how consistent is the density that you get from that and the data by overlaying them on these plots? And I just noticed here these I should have actually had a probability statement in here that I probably wrote it too high, so it was off the scale. So usually what I would do then is I can then take all of my posterior samples and calculate what fraction of those values are more extreme than the observed value. And that provides me with essentially a probability statement. So for example, in this panel in the upper left hand corner, you can see that the density pretty well straddles the observed value. There's probably a little bit more to the right than the left. So if I had to sort of ballpark what I'm looking at here, I think we're seeing roughly 60% of the predicted values are greater than the observed values. So you could say 60% of them are in a sense more extreme to the right than the observed data, but for the most part we're pretty close in. 80 milligram, similar, maybe slightly more extreme, but certainly not bad. Anyway, if you look across all of these, about the only one that might start making you wonder might be this 15 milligram, but since that's only 1 out of 10 and the rest of them are looking fairly clean, my reaction to the example you're looking at there is it looks like our model has been reasonably successful at capturing this. Let's see, what is it says my arrow is pointing to a blank space, probably because I'm having the bad habit of moving my arrow too much. So I'll try and keep that in mind. I'm jittering it around here, and your screens probably don't catch up too quickly, so maybe I should stick with putting red marks on things so that you can see them. At least I presume that's what the concern is. Let's see. It says I have a question here that says what does the zero density data mean in the distribution plots? Can you clarify your question there? I'm not quite sure what you're asking. Anyway, I'll move forward until I see a response come up there. So where was I going to go here? Okay, so for the most part, things look pretty good over here. Oh, I see one of the problems as I had pushed another button. Never mind. Anyway, so left-hand side, you see that for the mean peak. On the right-hand side over here, you see the same kind of plots for the area under the curve. And in this case, you can see sort of a similar pattern with maybe a couple of them a bit more extreme. You can see the 30 milligram here and the 60 are more extreme into the tails. But again, when there's a small number of them like that out of that many different dose arms, and there's nothing particularly systematic, I'd be more worried if I saw 30, 40, and 60 doing something funny. I might see that as systematic, but where it's a couple isolated ones, I probably wouldn't be too concerned. Let's see, what do we got here? Follow up on the question. Let's see, something about the points at 0 for the predictive distribution. I'm guessing what we're talking about, for example, is in the, I'm going to guess here we're talking about something. The question pertains maybe to the one we're looking at over here, where we've actually got for our 0 milligram, things actually seem to be centered right about 0. I have to, I actually haven't checked into that. I have to go back and look at the data to see if there's anything in particular going on there. And one possibility here is when we're talking about percent change or essentially when we're talking about this inhibition, and I believe it is possible for those values to go negative in here. So they're essentially bounded above by about 100, but they can go below 0, I believe. So if that's where your question lied, that's probably what we're looking at here. Okay, so again, what we're looking at on here, what would be a problem is if we saw a lot of these red dashed lines in here showing up well into the extremes, in these, well into the tails. And if we saw a number of those happening, we might question our model. Let's see, how far did I want to go here? Sorry for the jittering around there. I was trying to think if there was any other story I wanted to tell on this. I think that's about it. Well, another category of graphical checks that I usually don't quite think of quite in the same heading as the kinds of posterior predictive checks we've looked at so far, but you can represent some elements of the posterior distribution here, and that would be in residuals. Now, all of you probably worked with residual analyses of one form or another, and the basic gist here is not fundamentally different. About the only thing that you can make different, if you wish, is you can actually express the uncertainty in those residuals as part of this, because residuals in this instance are not single values, they are distributions again. So for any given observation, the model prediction is a distribution, so even though the data point is a single value, the difference between that data point and your prediction is a distribution. And one approach you could use to represent that in a residual plot would be to use something like lines representing prediction intervals. So in the examples I show here, let's take the left-hand group here. We're plotting the residuals, and in this case these are the individual residuals. In other words, I'm taking individual predictions, and that's what's being subtracted from the observed data. And then on the y-axis here, I have the predicted inhibition of factor 10a activity as a possible covariate for these, and I plot these here. Now, the reason why all of these prediction intervals show up as diagonals on here is because now I have uncertainty in both directions, because I've got residuals which have uncertainty and the predicted values have uncertainty in them. On here, the blue dots in this represent the posterior medians in this. Right hand side is a similar thing, but now I'm plotting the same residuals but versus in this case a trial design item in here, namely the observation times, and you can see those overlaid on each other. In fact, they're too overlaid. I probably should have stuck a little jittering in here so that you could see the lines for the individual data points here. Now having shown you this, I'll be honest, from a practical point of view, I usually don't bother throwing those lines in there. Most of the time I haven't found it's told me much more than just using something like the posterior medians and doing the residuals in terms of those. But it does point out that it is possible to actually represent these uncertainties as part of your residuals. In fact, the other, I guess, bit of pragmatism here is, stepping back here, I generally find posterior predictive checks like this and like the data-based ones here to be, more informative, I think, than residual analysis in most contexts. But there are times where you're trying to tease out issues of heteroscedasticity and that, where I'd agree that the residual analyses can offer some unique advantages. Okay, that was the posterior predictive checks. Did I ever, I never actually put a slide on here about, I had mentioned the quantitative elements of the posterior predictive check, and that is, let me step back to this, and in particular talking about things like a posterior predictive p-value, and actually we sort of touched on that, but not by giving it that name. When we start talking about the probability that the predictions are more extreme. In fact, it gets, I always debate, do you talk about it's the probability that the predictions are more extreme than the data, or the probability that the data is more extreme than the predictions? I suppose the former is probably the more rational statement here. But a posterior predictive p-value might fall into the category of describing it that way. So, for example, let's take one that does look a little more extreme here. Let's take this panel right here, the upper left-hand corner, and the one for the AUC. And so, for example, particularly if let's say I wanted to make some kind of a decision about whether or not, maybe whether or not the model was acceptable, and I wanted to set some sort of criteria based upon my ability to predict a particular statistic with, in a way that was consistent with the observed values. And, so in this case, we've got a whole collection of them, but for now, pretend the only one we're looking at is this one plot here. I might, for instance, put a criteria on that and say that I will only, accept the model if say the probability that the posterior predictions are more extreme than the observation, if that probability is less than something. Now you could either make it one-sided and talk about, say, only the probability that you're to the right of this line here, or you could do a two-sided one where you'd put a bound on the left-hand side too. But let's think of it one-sided for now. I might take a look at this and say, okay, well, what's the probability that the predicted values are greater than the observed one? And if that's, say, more than, let's see, which one am I doing? Actually, if that was, say, less than 0.05 or less than 0.025 or something like that, I might choose to reject the model and seek some alternative model to describe the data. So the posterior predictive p-value would in fact be that probability we're talking about. And in terms of the picture here, that would essentially be what fraction of my simulated, my posterior simulations fall to the right of this vertical red dashed line here. So that would be our posterior predictive p-value. In most cases, though, I find it in most practical modeling situations that we encounter where we're working with relatively complex nonlinear models like we often do in pharmacometrics, it's pretty hard to identify a single statistic upon which we'd want to do that. We're usually looking at something more like the picture we've got here, where we're going to have multiple outcomes, both in the sense of having, say, multiple treatment arms like this, but also multiple statistics even within each treatment arm that we want to look at. So it may be a little harder to set that kind of criteria. I suppose if forced to, we could come up with some composite metric based upon multiple statistics, like peak and AUC and maybe a minimum or something like that. But again, I sort of hesitate to set that kind of hard criteria unless I'm really forced to set that in some way, simply because there are usually so many different facets of model performance that I want to bring into the decision. Okay, so let's see, we hit our residuals. Okay, let's move on to another sort of general category of model checking or model evaluation in here, and that would be sensitivity analysis. And well, the first statement here is certainly not specific to the Bayesian world. The statement here that it's generally desirable to assess sensitivity of your key inferences to model assumptions in here. And the kinds of model assumptions you may want to evaluate would be things like your model structure, in other words, the functional forms of the likelihood and the prior distributions. There are quantitative assumptions that I may wish to evaluate. for example, values of the parameters in the prior distributions as part of this. What I'll focus on here is to talk a little bit about the prior distribution and sensitivity to choice of prior distribution, mainly because that's unique to Bayesian modeling, which is sort of our central focus here. So let's think about a couple of different contexts, both when you want your prior distribution to be essentially non-informative or the context where you want it to be informative. I mean, that's really a continuum, but the way you may view the problem of sensitivity analysis changes somewhat in those two contexts. So let's start out with the case where your intention is for the prior distribution to be, non-informative or weakly informative. In that case, what I'd like to do then is to assess whether I've actually picked prior distributions that meet that intent. Are they, in fact, relatively non-informative? Are my inferences, really, largely independent of that prior and almost completely determined by the new data? So one approach I would then do would be to compare the effect of different prior distributions on important inferences or predictions coming from that model, and the different prior distributions I'm going to look at are going to be other prior distributions that are consistent with my notion of non-informative or weakly informativeness. So as I say here, I mentioned I would use different priors that have different degrees of weak informativeness. For example, I might use normal distributions with a range of variances, but in particular with a range of large variances in here, all of which I think are consistent with the notion of being weakly informative. I also might explore what happens if I use different distribution types. For example, maybe I start out with a normal distribution with a fairly large variance, but what happens if I throw something else like maybe a t-distribution with various degrees of freedom instead of that? Does the fact that I'm dealing with a fatter tailed distribution make a difference? And if it does, why? If I really thought they were all non-informative, why is it influencing my key inferences? So again, it's looking at, and part of this is also just simply checking to make sure that maybe you thought it was non-informative, but maybe your choice of parameters for some of your priors wasn't nearly as non-informative as you thought, so you'll have to rethink it and alter them so that it really is non-informative. Then there's the case where your intention is for the prior distribution to be informative. Now in this case, your intention is for it to be informative. You expect it to influence the inferences. That was kind of the point. So you wouldn't, so a sensitivity analysis would not reject the use of an informative prior because it's actually influenced the inferences, because that was very much your expectation. However, there's still reason why you want to do a sensitivity analysis. You'd like to, it's desirable to assess the relative influence of your prior knowledge and new data on important inferences, if for no other reason to ask what's going to be the obvious question by somebody, which is, to what extent is your, are your conclusions influenced by your priors, and how robust are they to choice of prior? That way they know, both you and they know whether any arguments you need to make in defense of your model have to be made primarily upon what's contained in the prior versus the influence of the data or the overall model structure. So as I say again, the sensitivity to your prior distribution is not necessarily a bad thing. In fact, it probably isn't a bad thing. That's what you probably wanted. But again, it's desirable to know the extent to which the prior affects your inferences. What I suggest is you should explore a range of priors consistent with the range of knowledge and beliefs held by other stakeholders in the analysis. I suspect that many, if not most of us on the call here, are involved in contexts where you're going to be doing analyses that are going to be used to support various kinds of decision making for which you probably don't have direct control. You're probably providing information to other stakeholders who may hold greater decision-making authority than you do. So you need to provide some support for your priors, but also if there are differences amongst the stakeholders, for instance, members of a drug development team, in terms of what they believe are plausible priors, it's probably wise to do the analysis based upon a range of priors consistent with that range of knowledge and belief by those stakeholders. Let's see. I'm trying to remember, what did I have here for an example here? Okay. One direction you might want to consider is let's say you're in a context where the focus is to evaluate the probable benefit of some particular treatment. So what I would do is I would start out with what I think is my best choice of prior based upon something, whether it be based upon some sort of consensus, some sort of past data, something which I think is defensible anyway. But then I would also consider priors that reflect both more and less skepticism than the one that was used for the primary analysis. And particularly if, let's say, the primary analysis concludes that the treatment is more beneficial than a comparator. And as part of the process of supporting that inference then would be try to identify the least skeptical prior that would make the conclusion unconvincing by whatever criteria that you're applying here. So you would try a range of priors. In some cases it may just be a matter of taking whatever parameter or parameters are most responsible for determining the effect size or the difference in effect size between this new treatment and whatever you're comparing it to. You would modify that by shifting it to maybe ever smaller differences, and you find out, okay, well, what's the smallest difference there that would essentially negate the conclusion of the primary analysis, and then look at that and say, okay, is that skeptical prior plausible? Is it plausible to you? Is it plausible to the other stakeholders? Now the easy case is if it turns out that the least skeptical prior that negates that your original conclusion is clearly implausible both to you and the other stakeholders. That's an easy call. Then you can basically go forward and say, yes, the quantitative results are influenced by the prior, but the only prior, the least skeptical prior that results in a failure to show benefit is just absurd. Then you've made your case. If, on the other hand, the least skeptical prior is in fact plausible, then you have to look harder at the prior and see what additional information you can bring to bear to support the original prior we're using, and also, in fact, ask, is it in fact supportable compared to that skeptical prior that negates the inference? So it's, so again, it's part of a process of either challenging or defending the particular conclusions that you reach with the primary analysis. Okay, let me take a breath there. See if anything's popped up on the question board. No, nothing there. Okay. Let's go to sort of the sort of related topic, which is the topic of Bayesian model comparison. So actually what I've told you up to now is more this notion of treating the model development process is more of a sequential one, where it's not so much that you are making a comparison as much as you are evaluating your candidate model and deciding whether or not it's acceptable. So in a sense you're not competing with a specific alternative. However, there's also, there's certainly going to be contexts where you in fact will be comparing to alternatives, and so how do we go about that? And this is another area where there's a fair amount of literature in the Bayesian world about that, and various different strategies that have been talked about. But and I'm going to sort of take one particular path, but at the end I'll try and point you to some other paths that people have considered. Okay, so first of all, competing models can be compared with respect to the very kinds of model evaluation tools we've already talked about, namely things like posterior predictive checks, and also again comparing with prior knowledge, what I termed here consistency with other substantive knowledge. Are both models equally consistent with prior mechanistic knowledge, for example, as part of your evaluation. So part of it's a check against data again, part of it is a check against other knowledge. Some specific metrics that are available for comparing models primarily with respect to their performance and analyzing the available data. One would be to use expected deviance as a metric for doing that. Another one, which is derived related quantity, is something called the deviance information criteria, or the DIC, which I suspect most of you have worked with things like Keiki's information criteria, or the Schwartz information criteria, and so on. Most of those involve some measure of the likelihood corrected for model complexity, and that's basically what DIC is also, and I'll give you more specifics in a minute. So let's take a look at those metrics. Okay, so let's start out with expected deviance, and viewing it as a sort of a measure of prediction error. Well, first of all, reminding you what deviance is. Deviance is minus 2 times the log of the likelihood. So here I've just written it out and giving us some symbolism to work with. So I'll use this capital D, which depends upon both our data and our parameters here, y and theta. So that just equals minus 2 times the log of our likelihood function, our p of y given theta. As I say, it's like the non-mem objective function, except that it is in the form of a posterior distribution instead of a single value. And recall again, with non-mem or other maximum likelihood methods, usually the likelihood value that you're working with is the value of the likelihood evaluated at the maximum likelihood estimate, where in this case the deviance is being evaluated at all the values of, at the posterior distribution of our parameters, so you get back a distribution. Now, a couple of metrics that you could imagine using then if you were looking for some sort of single valued metric for model comparison. One would be to calculate the deviance at some point estimate, very analogous again to the maximum likelihood approach. So for example, you might plug in the posterior mean. So that's what this symbolism is intended to show, where you take some point estimate, I just called it theta hat, which would be a function of your data. So again, theta hat could be a posterior mean or a median, or I guess more classically it might actually be a mode. So you might take the posterior mode for those values. And then you calculate the deviance at that. So again, you calculate the likelihood at that point estimate, take the log minus 2 times the log of that. So, and here I'll just call that d theta hat. Or you could do the expected value. So, and here I'll just call it d average. Again, it's going to be a function of your data. So you calculate the deviance then, and of course that's conditioned on y, because so it's the posterior distribution of the deviance, and then you take the average over that. Excuse me. So you're taking an average over the entire posterior distribution. And the expected deviance seems to be more generally regarded as the better summary of model error. and more directly related to predictive performance. And that's something you've already seen in the outputs that you've gotten from the examples. Is generally I've had them set up so that you're collected the deviance as part of the information, and in fact by default WinBUGS always monitors deviance, so that you can always access the posterior distribution, or the MCMC samples of deviance from WinBUGS. So now, just like the typical, a least squares objective function or a likelihood-based objective function, as you throw more parameters at things, you make the model more flexible. It will almost certainly, it will usually fit the data more closely, and so the likelihood will tend to go up, and correspondingly our deviance, or minus 2 times the likelihood, will tend to go down when you increase model complexity but keep it roughly the same form otherwise. So one problem you can run into is if you just look at expected deviance, you have the risk of model overfitting as a result of that. And of course, if you end up with overfitting, you have a model that may actually have pretty poor predictive performance, because you've basically overfit the data at hand, but it may not generalize to inferences about future data. So how do we try to offset that tendency? Well, the offset to that tendency is to try and incorporate some sort of measure of model complexity to offset the deviance itself, and that's where we're going with the deviance information criteria. So let's say that the objective is to select the model that has the best predictive power, the best ability to predict new observations, not just to fit the existing ones. Then it's the expected predictive deviance that would be a good criteria of fit. And what I mean by expected predictive deviance, it would be if you you take some theta that comes from your model based upon having fit some previous data, y here, and let's say we want it, but now what we're going to do is we want to predict new data that was not used in order to fit the model, and we're going to call that y pred. And in particular right now, the y pred are going to be predicted observations from the same design as the original data, but we're now making forward predictions for things that we haven't observed. And if we take the expected value of the deviance using that then is a measure then of predictive performance. So it's now the expected predictive deviance that we're using in here. And if we accept that as the primary notion and suggest, okay, that makes sense, because now we're essentially talking about external predictions as part of this, then how might we actually estimate such a quantity, given that we don't actually have numbers that we can plug directly into this? Well, the suggestion here is we approximate that quantity, and it's been shown, there's publications out there, I think David Spiegelhalter is the primary author on these, that shows that the expected predictive deviance can be approximated by this thing called the deviance information criteria. So got that approximation notion, and this deviance information criteria is defined according to the stuff on the right hand side here. It ends up being 2 times the expected deviance minus the deviance for the point estimate theta hat, and okay, here actually didn't say explicitly here, but I think generally we're talking about theta hat in this instance being the evaluating the deviance at the expected value of your parameters. And the way you generally see this written up as being the sum of the expected deviance plus this P sub D here, which is argued to be an estimate of the effective number of parameters. The reason why it's not exactly the number of parameters is because when we get into hierarchical models like we commonly use in population modeling, not all parameters are created equal and play the same role in these things. So you may have a certain number of sort of top level parameters, your fixed effects and variances. So you've got like fixed effects describing things like population means of various parameters, but then you also have additional complexity coming in from the hierarchy that determine things like inter-individual variability, and that adds to the apparent number of parameters. On the other hand, each one of the individual sort of subparameters, like individual specific values of parameters, don't play as nearly a dominant role as those higher level parameters, so they in a sense need to be somehow discounted, and it was argued that essentially this metric here provides the appropriate discount, where we're looking at the difference between the expected deviance and the deviance at the expected value of the parameters. And so in the end here, then we end up with this thing where we can just view then DIC as, as the expected deviance here adjusted for model complexity over here. So you get the more complex the model, the more penalized that expected deviance is, because the effective number of parameters would tend to grow as the model complexity grows. Okay, so having gone through all of this, let's go to the next thing here, is then how would you use it? Well, the general notion here is that all else being equal, and all else being, for instance, other model evaluation criteria, where you might be looking at posterior predictive checks and so on. And so if you have two models that appear to perform similarly with respect to some of those other metrics, you would probably choose the model that has a lower DIC in here. And so in practical terms, how would we do it? Well, it turns out DIC can be estimated from posterior samples, and I don't know why the I is there. I don't think it's supposed to be there. It can be estimated from posterior samples according to the sequence here. So first of all, we go ahead and calculate our expected deviance here, and we do that using, you've seen the deviance values that come out of the MCMC sample. Well, we just take the sample mean of those values, and then to get an estimate of that effective number of parameters here, we've got a relationship here that involves taking essentially it's a variance type term here, where we're taking all of our deviance terms here and subtracting from it our average deviance. So you've got a square, so you've kind of got a variance of that, and you take half of that, and then finally the DIC is the sum of those two things. But it turns out, of course, that where are we going here? What am I missing? No, that's everything. That the easiest thing to do is if you set up WinBUGS correctly, it can go ahead and calculate it for you. In addition, there's actually a coda command for calculating DIC after the fact. But it uses a somewhat different method, and in fact, if you compare the two, what you'll often find is, though the expected deviance values you'll get are the same, sometimes since they use a somewhat different algorithm to get at PD, you'll actually get some differences between the two methods. Suppose you could use the two to sort of as a cross-check. Let's see, I guess let me mention a little bit about what we're not covering that is out there in the literature. DIC seems to have gathered some favor, I guess, in the Bayesian community compared to some of the other ones, but there's a lot of other these so-called information criteria. Again, these are all things that are based upon some adjustment to the deviance or some other measure derived from the likelihood. So you've got things like the Akaike information criteria, Bayesian information criteria, the Schwartz, and there's a few others out there too. So there's other options out there. And there is another fairly large stream of literature out there that talks about use of something called Bayes factors, both for model comparison and for model averaging. In the model averaging case, it's sort of a two-step strategy for doing the sort of mixture modeling approach I mentioned at the outset in there. But in addition, sometimes the Bayes factors are simply used for model comparison. Again, there's a fairly sizable literature. It's not talked about much in the Gelman et al. Book, but I'm trying to remember. There's the I'm trying to remember the name of the authors now. There's one where it's Brad Carlin and I forget the co-author that have a text at a similar level to the Gelman book that spends a fair amount of time on it. And again, there's a lot of primary literature out there on the topic, and it's one that's I haven't dug into very far myself, but might be worth exploring if model comparison becomes a common issue in your own work. And there's certainly a range of other sort of model averaging or mixture model approaches that exist out there for working with some of these. Well, we actually scooted through that material a little faster than I anticipated. We might actually do a few other things then, but let me take a breath here and see if any questions have cropped up, especially if I've run through this a bit too fast. Let's see. Mike asks, does the FDA have a stance on skeptical priors? And I guess the short answer is I don't know. I haven't dealt directly with them around that, particularly on the drug side. And the drug side also has less experience in dealing with Bayesian approaches in general. If I was to hunt this kind of information down, I'd actually probably look to the devices side to see how that's been dealt with in that context, because there not only have there been substantial use of Bayesian methods, but they've been Bayesian methods that take advantage of informative prior distributions. So, again, the main answer I give you there, I'm afraid, is an I don't know. Okay, why don't I go ahead and start moving on here, or did I just see another one crop up here? Let me double check. Could I give an example of sensitivity analysis? Unfortunately, the best way of giving you an example would be to give you a worked example. Because I'm not sure I can, that it would do a lot of good for me to try and get more specific and just sort of a verbal description. Let me put a note down to myself and see if maybe I can come up with something for next time, because again, I'm not sure trying to come up with sort of a verbal description would be particularly useful as part of that. Yeah, but I guess the short description in here would involve identifying a range of priors that, again, it would depend upon the context, whether you're trying to be non-informative or whether you're trying to be informative. But let's say in the non-informative case, one of the simplest examples would be simply, you start out with whichever ones you had as sort of your primary choice, and then let's say let's say most of your priors were normals with large variances as an attempt to be weakly informative. The simplest approach to a sensitivity analysis would be to try, a minimum would be to do two other cases, one which had a larger variance and one which had a smaller variance, but was still relatively large compared to what you think represents informativeness. You would redo the analysis using those different priors, and then ask, okay, what were my primary inferences based upon this model, and to what extent were those inferences changed? So, for example, if you have a parameter in your model that is that serves as your primary measure of, say, the effect of a particular treatment, then you might look strongly at things like, say, credible intervals for that particular parameter, or derived quantity that describes the effect size, and say to what degree is that influenced by those different priors. And again, if your intention was to be non-informative, and if that credible interval changes markedly as you move the prior, then you may have to reevaluate your priors and possibly other aspects of your model, because it apparently isn't being consistent with your intent. On the other hand, you may do that and you find it moves very little and is unlikely to have any substantive effect upon your inferences, and at that point you've done your due diligence in checking the model, and you also have some evidence to help support the model in the presence of criticism from others. So that isn't being much more specific than before, but as I say, I'll take a note, and maybe I can come up with something illustrative for next time. Okay, oops, wait a minute, there's supposed to be one more slide in here. Did I grab the wrong slides? I did. Excuse me, I think I grabbed the wrong slide deck here. Fortunately, I don't think anything else has changed. Oh, yes, it did. There was an important piece that was missing. I should have caught that. Well, that's good, because it's worth going over, because it'll support our work. What did I do? I must have used the one from the... Okay, let me take a look again. Now, this has to be the right one. As I say, I added some slides and I didn't see them. There we go. Convergence. There we go. Let's make sure I got the right one this time. Yeah, okay. I was missing a piece. Okay, I'm not sure which one I opened, but let's open this one. I don't think I'll do a quick run through just to make sure, but I don't think any other content was different other than the... Okay. I think everything else up here was the same. Yes, okay. Yeah, there was actually a bit of how-to in here that I wanted to show you. And this is actually the added material. I don't know if all of you got your email mentioning that the revisions that I made, but that's what I was missing. Let's actually go back to what we were talking about back here when we were talking about doing the this type of posterior predictive check, where we're looking at comparing some derived quantity. Here in this case it was the peak factor 10A inhibition and the mean, and the AUC for the factor 10A inhibition. And what I wanted to do is show you the mechanics of actually constructing something like that using R. One, because it's handy for you to have that, and two, because I'm going to give you a homework assignment that involves doing exactly this kind of problem. In fact, it's essentially to replicate what you're looking at right here. At least that's part of it. So what I give you here is a couple of slides here which provides an R template for that type of posterior predictive checking. So talking about a template then to do posterior predictive checks for the mean of some individual data summary. And the one that I'm illustrating here is where I'm taking the area under the y versus time curve, where y is some quantity. And so this is just illustrating the process. So I wanted to give this as something you can build on. We probably don't need to go through all the nuances here, but let me pull out the key parts here. So the first part you've actually seen before in previous examples, where I just take our collection of MCMC samples and just grab the subset of that which pertains to our posterior predictions. Then in this case, I want to start by calculating the treatment arm mean for our statistic, the statistic being our area under the y versus time curve. So what I want to do is first of all, for every individual, I want to calculate the area under this y versus time curve. I'm just going to use trapezoidal rule for doing that. Then for each treatment arm, for all the individuals in a given treatment arm, I'll take the mean of that. So in the end, I will have one mean per treatment arm in this. So right here, I start out this line right here. Aggregate, I don't know if you've ever worked with it, but aggregate basically applies a function to, you can think of it as applying a function to a column in a data frame, but it breaks up that column in there by whatever appears as a list here. So this is going to take, first of all, what it's doing is it's taking my list of rows, and I'm just going to say 1 up to however many rows I have in my data file, and my data file here is going to be called xdata. I then subset that by both subject and treatment in here, and then I'm going to apply a function to those subsets. So I'll pass this I is going to be the indexes that it gets when it breaks up that, passes it to our function. The xdata, I'm just passing the whole data frame in. And then I'm going to use a function which this function's actually contained in that BUGSModelLibrary script for doing simple trapezoidal rule. So it's just going to take, in this case, the time values and the y values here. So obviously I'm assuming that xdata contains a column called time and a column called y, as well as a column called subject and treatment. In fact, that's, I think, all you would need for this script to work in here, and then also telling it that xdata is xdata, basically. I'm giving, and now what that's going to do is it's going to create a new data frame, which is going to have a number of rows equaling essentially the number of subjects in the data set. It'll have a new column in it that'll contain the result of doing the area under the curve calculations, and here I'm just giving it a name, and for generality I just called it stat. And then I go a step further here and take that and take means over over all the treatments. So it's taking mean over, well, it's actually it's mean by treatments. So it's a mean over all the individuals within a given treatment arm. So now I'll have a new data frame here, which is going to have, what will it have? It's going to have a column for treatment and a column for stat inside there, and that stat will be the mean area under the curve for the corresponding treatment arm. So I've done that now. What that describes is doing it for the data. The next step is to do that very same thing, but to do it for each MCMC sample. So let's say, I forget how, for our example before, where it was our hands-on example 2, forget how many MCMC iterations we did, but you take however many of the iterations you saved, and there for each one of those iterations you're going to generate a full set of these mean AUC values. So in the end you'll end up with a distribution of AUC values for each one of the treatment arms. So most of this is just going through, and this X1 is just generating a framework to put the predicted values in. I just take the original data set and only keep the values corresponding to a single subject and treatment in there. I guess I ordered it by subject, and then this step is this actually takes a little bit of time. It's not too awful, but it takes, because you'll notice it's got nested applies. There's an S apply here and another apply here. The one on the inside is doing exactly the same thing as we did up on top with the aggregate statement, where it's going through and calculating the areas under the curve for each treatment arm in here. The outer one is actually looping over all of the rows of our posterior matrix in here, so it's going through all the posterior samples. So in the end what you get is an object. Well, let's see, it goes through here that, well, I'm trying to remember, where do I use X2 here? Okay, so in fact here it's not even taking the mean yet. I'm just getting all of the area under the curve for all of the individuals for all of the MCMC samples, and down here is where I finally pull it together. Embedded inside this construction of a data frame is an apply step here, which is taking the means over the individuals within each treatment arm. So anyway, this is, if you want a little sort of I guess course in, I don't know, advanced or intermediate R, this would be a good one to use to get a handle on how to use some of these apply related functions like apply, sapply, and aggregate to generate some of these things. So in the end you'll end up with two objects that we want. We'll end up with stat, which contains our the AUCs for the mean AUCs for each treatment arm based upon the observed data, and then stat pred, which includes the essentially the empirical distributions of the for our posterior predicted mean AUC values for each treatment arm. Then the next step is we've actually got everything we need to do the plots, and that's what we've got here. What I'm showing is the code, and on the right hand side the product of that code. And actually in this one too, you'll notice, in fact, maybe even before I show you the code, let me show you what we were trying to create. So you've actually saw this before in the previous plot. The one thing I did here is I fixed the bit of actually showing the calculation here, where you can see it says the probability that the predicted values being greater than or equal to the observed is a particular value. In this case came out to be 0.05 in here. So I do that for each one of the panels in here. Otherwise it's the same as what you saw before, and a panel corresponding to each one of the treatment arms in here. The first way I do it is exactly what you saw before, where I use the density plot statement. This is one of the plotting types within the lattice package for plotting. So here I set it up first where I take well, first of all, I'm using stat pred as the data set it's working with. So the basic statement where it says density plot for the object stat broken up by treatment. So that's why you get a separate panel for each treatment arm. That is what's creating the density plots that you see on there. Most of the rest of the code in here is being used to generate that vertical line for the observed data and the statement here about the probability of the predicted being greater than or equal to the observed. So anyway, so we come in here, we define our panel function here. The first one again creates the density plot itself. Then we go in and find out, okay, well, for that particular panel, which treatment is it doing? So this is pulling that out. This subscripts object is a predefined thing within lattice. So that's a trick here for getting the treatment identifier, which in turn I use to pick off the appropriate line within the oh, I see a typo. That should just say stat, not stat. In here, actually, or should it? No, actually it should be stat $stat. Anyway, that's a typo. It should be stat $stat, and then the right hand side you can see it says stat $treatment is equal to treatment. So it's pulling off the row that it wants, so it's going to get a single value here which corresponds to the mean AUC for that particular treatment arm. And then right here, the next line here where it says panel AB line is creating our vertical dashed line here in red that occurs at the value of the observed value of our AUC. So that generates that. The next mess in here is going through and it's both plotting and calculating the probability that the prediction value is, probability of predicted values being greater than the observed, and the actual calculation itself is happening right here, where I actually just take the x values that actually correspond to the posterior predictions and the stat obs, and the x values is a big vector, stat obs is a single value, and I'm simply adding up this logical. So it says x greater or equal to stat observed, which will equal 1 if it is and 0 otherwise. So when I sum it up, it'll be a count of how many of those x's are bigger than the stat observed, and then if I divide it by the length of x, I will get the fraction of them which is greater than or equal to stat observed. And then the rest of this nonsense is all formatting in order to show it correctly on the plot, as you can see on the top of each one of those panels. I don't think there's much of a story to tell about the rest of it. Yeah, most of the rest of it is just formatting. That's one way of plotting it. Some people prefer histograms, and it turns out to modify this and create a histogram is fairly trivial. And that's what I show here. You can see on the right hand side the equivalent plot but done as a histogram, and the main difference here you can see is the word histogram shows up here and here. And the only other little trick that you have to throw in here, where is it? Is right here. To say breaks equals null, and the only thing that is needed for is if you don't, what happens is you end up with histograms with like 2 bars in it, because the values on the x-axis are very different as we go from placebo here all the way up to these relatively large values for the high doses. So if you don't put the breaks equal null, it basically ignores this statement and does not let the x-axis be different for the different panels. So that's just a little extra trick that in fact I didn't know until today. Yeah, I think that's pretty much the story for that, and this will be a suitable template then for one of the things I wanted to assign as part of your homework, which we'll scoot down to. I don't think I changed anything there. No, good. There we go. And here's the homework. And there's a couple of pieces to this. Okay, let's start out. So what I want you to do is implement a few different graphical posterior predictive checks for the model that you did in hands-on example 2. The first one, in fact, let me scoot right back to the picture. Not that one yet. Oops, I went overshot. There we go. The first one is to essentially replicate what you see right here on the right-hand side. Okay, the idea then is to for, take a range of values on the x-axis here, range of values of plasma concentration, and generate the posterior predictions for our percent factor 10A inhibition along those, so that you can then generate the posterior mean and 90% credible intervals then based upon those posterior predictions. Now, the reason why, well, let me see if I can explain why that doesn't just follow naturally from the original analysis. In the original analysis, each individual had his own unique plasma concentrations in there. It's not like they were, that the concentrations were not a design element that was fixed at the outset. It's just something that happened given the results of administering the dose to the individual patients. So if you were to try to take the observed concentrations along the x-axis versus the y, what'll tend to happen is you won't have a good representation of all the concentrations as you move from left to right on here. You'll have this odd mix. What you'll find is you'll end up getting something similar to this, but it'll be pretty noisy, and it won't be a very clean representation of these posterior predictive intervals as you go across on here. Because in effect what you're doing is taking all these posterior predictions corresponding to each one of these points in here and trying to sort of lump them together. And that tends to be more difficult. What you're better off doing is actually pre-specifying a range, essentially a grid along this range here. Pick something like, say, 0 to 1500 nanograms per milliliter. Is that what I did before? I don't know if it looks like it might have been 1600 there. Take a range like that, break it up so small enough so that you can get relatively smooth curves out of it in there, and then for each one of those you use the posterior distributions of all your parameters to do simulated values corresponding to each one of those hypothetical values along your grid of concentration values. So it's like a separate simulation apart from the ones we did before. Let me step back to our homework assignment here. Okay, so the idea here is I want you to do posterior predictive checking plots then for your posterior predictions of factor 10A inhibition as a function of drug concentration. And these should be the population predictions now. So we're talking about predictions for new populations, not individual predictions. And then you overlay the posterior medians and 90% credible intervals in the data on the plots. And as a learning exercise, I suggest you do it two different ways. And depending upon the context, one way may be more efficient than another, and there's no general rule on this. One approach is to actually generate the posterior predictions inside WinBUGS as part of the model fitting process. The other one is instead to generate the posterior predictions in R, where you take your posterior predictions for posterior values for all of your model parameters, and you write a function that essentially replicates the model you did in WinBUGS, and you simulate from that by looping over all of the all of the essentially rows in that posterior matrix, and then calculating the quantiles across those. I would say if you get stuck on this, if you go to the, let me step out of this here and pull up. Actually, let me pull it over here. Realize the wording's a little tiny here, but let me see if I can grab it here. If you go to the hands-on 2 example, and if you go to the original one, which recall last week we kind of hid away and built a separate one, but if you go to the original solution, which you'll find either here or down in the solutions sorry, down in the solutions folder. Let me bring this up and okay, let's make that bigger. Okay, let's scroll down. Actually, is that where I want to do it? Well, this is not where I wanted to show you. I want to show you this part of it, the BUGS model. I suppose in a sense I'm showing you the solution to the problem, but I need to give you some lead on it, I think. Is this the right one? Yes, it is. I'll cut that out. There we go. Okay. If you recall before, you would have written a model that looked pretty much like this first part up here plus the priors. The trick here that I'm suggesting to you is you actually incorporate another loop which is there for no other reason than to do simulations at a set of fixed values of concentration that you put in here. Because keep in mind, your model here is not modeling the concentration. The concentrations are just treated as independent variables in this case. So the idea here is you're going to generate you can loop over, say, some range of values here. The way I've written this is nsim is a quantity defined somewhere in the data set, which might be something like, anywhere from, say, 20 to 100 values, and that has to do with how finely you're going to break up the concentration range. You also need to specify the range of concentrations, so like a minimum and a maximum, which in this code is, I've given the name Cmin and Cmax in here. And all this first line is doing is generating a set of what it calls CSIM values here, in other words, simulated concentration values, which is nothing more than a grid equally spaced going from Cmin to Cmax, such that in the end you'll have nsim values of that type. And then the rest of this is doing exactly the same thing that you did in the model. Basically everything that you do inside when you calculate fxa.pred is what you do inside here. And that includes both the inter-individual variation as well as the residual variation component. So when you get done, you have a new set of values that have been calculated in an equally spaced range, equally spaced group of concentration values, and then you can take those values, get the median, posterior median, and 90% prediction intervals, and make a plot like the one we were just showing here. Okay, where am I going? View. So that would be doing it with bugs. So you would end up making sure you have to make sure you monitor the values you simulate. So you collect those values, you read them in along with everything else, and you can make a plot like this, using this similar approach to what you've seen in the other cases for using apply to calculate the medians and fifth and 95th quantiles in here. Now the other idea here, go back to our assignment. Over here, the other idea then, as I say, was to do the same thing, but instead of doing those simulations within BUGS, do them within R. So that one, if you like, you can consider that kind of the advanced topic here, since you don't have a direct example to work with. And we'll spend time on, I guess, on Friday going over, Friday or Thursday? Thursday, I guess, going over that. But anyway, try and do it in R, and it's worth having both of those approaches under your belt. And it comes, and which one you would choose in effect depends upon how expensive the calculations are in order to do the simulations. If they are computationally expensive, then you probably don't want to do them inside the MCMC runs, particularly if you're doing thinning, because that means you're probably doing more calculations than you actually need to for your work for your work as you go. So it'll probably cost you even more if you do it in WinBUGS. On the other hand, if the calculations aren't very expensive in the sense of taking a lot of time, you don't lose much by including them in WinBUGS, and it has the advantage that you're not trying to write the same model in two pieces of code, which is always fraught with error. There's at least a potential for error if you do that. On the other hand, in cases where the calculation is kind of on the expensive side, then I would recommend doing it within R and only calculating as many simulations as you need within that context. Okay, so that's that part of the problem. The other part of the homework exercise is to do pretty much what I was just showing you a little bit before, which is to do our posterior predictive checking plots for the mean peak and mean AUC factor 10A inhibition, and do that by treatment arm. Leave it up to you, whatever your preference is, whether you do it by density or by histogram. But pretty much what we're talking about doing, step back up there also, is replicating exactly what I've shown in this plot here, or in this one. So you can use what you see on the left-hand side. Here's a template. But the only thing you should probably have to change will be some of the naming here. So you'll have to use names that are consistent with those that are in your data set and in your model. Okay, I think that was the whole kit and caboodle there. Let's see. Yeah, I think that's pretty much it. Any remaining questions or requests before we sign off? Let's see, I think I saw a blip in the question meter here. Okay, I seem to have left a big mess in somebody's mind here. Okay, so the request was to get the recording up as soon as possible. I'll make every effort on that. Just so that you understand what the issue there is I'm in North Carolina, and everything else is in Connecticut, so it takes a while for me to upload a gigabyte or so of stuff here, and that is part of what tends to slow things down sometimes. But also, in the meantime, feel free to ask any questions that either here or via our usual forums here to help clear up whatever big mess in your mind there may be here. Okay, let's see, so far, unless somebody's typing a long one here, I'm not seeing anything additional come up here. So if, for the rest of you too, if I've left more confusion than answers here, please, there's two things. One, if there's specific questions I can answer, great, please pose them. Also, if you found that for some reason this lecture was particularly difficult and incomplete in your mind, please let me know that so that I can improve it in the future and perhaps help clarify things next week. So I guess until then, I'll say goodbye, and we'll try and get this up on the web as soon as we can. Look forward to seeing you later this week. Bye for now.